Lesson 2. Basic Acoustic and Traffic Noise Concepts. This lesson will cover the basic of acoustic and traffic noise concept used in evaluating highway traffic noise, including information on basic concepts of sound and noise, such as frequency, time, and magnitude, decibels, A-weighting and adding decibels, noise level descriptors, sound propagation, shielding, and noise barrier placement. What is noise? Noise can be defined as unwanted sound. And if you have teenagers like me, it might be just the sound of your voice. What is sound? Sound is a sensation produced by stimulation of the organs of hearing by vibrations transmitted through the air or other medium. There are three basic dimensions of sound: the magnitude, frequency, and time. The magnitude, also known as amplitude, is the loudest of the sound. This is represented in the graphic below by the distance the waves depart from the center line. The frequency, also known as the pitch, is the number of cyclical crests or variations, known as wavelengths, per unit of time. The distance between the crests of waves determine the frequency. Generally, the frequency is expressed in cycles per second. The metric which expresses the frequency is known as hertz. A wavelength is the distance between 2 points of the same phase in consecutive cycles of a wave. It is measured in the direction of propagation. Note, the period or distance between waves is what determines the frequency. A high frequency has closely spaced waves. Conversely, a low frequency has waves further apart. Of importance, low frequencies, which is depicted by the bottom of the two graphs, travel further than high frequency waves, which is depicted by the graph on top. The second dimension of sound is time. Noise is described based on its sound intensity over a given span of time. The illustration shows 4 different types of noise. A constant noise such as a fan is depicted in the top left graph. A pile driver is depicted in the top right graph. A single vehicle passing by is depicted on the bottom left graph, and random traffic is depicted on the bottom right graph. The magnitude is the intensity, or the loudness, and is what can be measured. The sound energy emitted per the unit of time is called the sound or acoustic power. It is a sound measured at a point in space which is a certain distance from the source of the sound to a receptor, or the recipient of sound. In other words, sound power is the source, and the sound pressure is the effect. Sound pressure is measured in sound pressure level, named bells. The sound pressure level is the log of the square of the ratio of pressures. Since a decibel is 1/10 of a bell, the resulting equation is what is displayed on this slide, where P sub 1 is a sound pressure, and P sub 0 is a reference pressure, which is standardized as 20 micropascals. Sound is measured in decibels with a sound level meter called a dosimeter. To give you an idea of what the standardized sound pressure is, 1 Pascal equals 1 Newton per square meter. 1 Newton per square meter equals 1 kilogram meter per second squared, which is equal to 0.000-14504 pounds per square inch. 1 micropascal equals 1 times 10 to the negative 6 pascals. 20 micropascals equals 20 times 10 to the negative 6 pascals, which equals to 0.0002653 pounds per square inch. This is the threshold of human hearing. The use of micropascals reduces the large number expressed in pascals. Sound pressure levels are expressed in terms of the reference sound pressure in bells, named after Alexander Graham Bell, by the following formula shown on the slide. Sound level meters are designed to give readings of sound pressure levels and offer a selection of frequency weighting networks designated as A, B, C, D, and Z. A-weighted is weighted for human hearing. B and D have fallen into disuse. C-weighted is the standard weighting of audible frequency. Z weighting is a flat frequency from 10 Hz to 20 kHz and is not weighted at all for the human ear. The human ear is much more sensitive to mid-range frequencies between 1000 Hz and 6300 Hz and is less sensitive to very low or very high-pitched sounds. However, human hearing covers the frequency range of 20 Hz to 20,000 Hz. And depending on the weighting network, the meter calculates the measurements to ensure it is measuring what you actually hear. A decibel is a unit of sound pressure level which denotes the ratio between two quantities that are proportional to power. A decibel is not an amount such as a weight or distance. Of note, it is possible to have negative decibels, which are those that are below the threshold of human hearing. This is possible since the reference level is the threshold of human hearing. This slide shows an illustration that used sound pressure levels in micropascal units on the left, the use of decibels on the right as a logarithmic expression of the sound pressure levels allows the use of much smaller numbers. Note, the threshold of human hearing of 20 micropascals is at the bottom, which is used as a reference point. A weighting is a frequency weighting network used to account for changes in sensitivity as a function of frequency. This weighting network most closely approximates the way the human ear perceives sound. This slide shows a comparison between A, C, and Z weighting. Notice how Z weighting is a straight line because it is flat from 10 Hz to 20 kHz. C weighting follows the frequency sensitivity of the human ear at very high noise levels and is commonly used in workplace noise and/or OSHA requirements. A weighting is weighted for the human threshold of hearing. The meter adjusts sound pressure levels up or down based on the frequency and weighting filters. Due to the logarithmic nature, the amount of acoustic energy loss is not proportional to the sound level reduction. Remember, a logarithmic scale is used to express a wide range of numbers on a nonlinear scale, which means the difference between 3 and 5 is not the same as the difference between 20 and 23. Since we are dealing with pressure ratios, a 10 decimal increase actually represents a 10-fold increase in intensity. A 20 decibel increase is perceived as 4 times as loud, but is 100 times the acoustical energy. This table provides examples of acoustic energy loss in relation to a sound level change and relative loudness perception. As shown, a 10 decibel decrease can be perceived as half as loud, but has a 90% acoustic energy loss. Furthermore, because of the logarithmic nature, decibels from multiple sound sources are not added together arithmetically. 50 decibels plus 50 decibels does not equal 100 decibels. This table provides guidance as to how to add decibels from multiple sound sources. For example, when 2 decibel values differ by 2 or 3 decibels, add 2 decibels to the higher value. 74 decibels plus 71 decibels equals 76 decibels. Now let's try adding the following decibel levels together. 75 decibels plus 68 decibels plus 88 decibels plus 82 decibels, and finally let's add 79 decibel, which equates to a noise level of how many decibels? For the first step, we have to arrange the decibels in order from lowest to highest. Next, the tables should be added in pairs using the table as a reference guide and starting with the smallest 2 decibel values. You have to take into account that when 2 decimal values differ by up to 1 decibel, you add 3 decibels to the higher value. When 2 decibel values differ by 2 to 3 decibels, you add 2 decibels to the higher value. Between 4 and 9 decibel difference, 1 decibel is added to the higher value. And for everything above 10 decibel difference, you should just use the higher value. Therefore, 68 decibel plus 75 decibels equal 76 decibels. Then 76 decibels plus 79 decibels equal 81 decibels. Following this pattern, 81 decibel plus 82 decibels equals 85 decibels. And finally, 85 decibels plus 88 decibels equals 90 decibels. Let's try another example. How many cars at 66 decibels would it take to double the sound? First, remember that an increase of 10 decibels is perceived as doubling of sound. 66 decibels plus 10 decibels is 76 decibels. So how many cars at 66 decibels does it take to reach 76 decibel, or perceived doubling of the sound? So we have two cars at 66 decibels, which would give us 69 decibels. Add in a third car, and we would have 71 decibels. A fourth car would give us 72 decibels. A fifth car would give us 73 decibels. A sixth car at 66 decibels would give us 74 decibels. A seventh car would give us 75 decibels. And finally, an eighth car at 66 decibels would increase the decibel sound to 76 decibels. Thus, it takes a total of 8 cars at 66 decibels to double the sound. Additionally, note that if any additional cars were to be added, 0 decibels would be added because the 2 decibels differ by 10 decibels or more. Sound level descriptors are the various metrics that are used to describe noise under various conditions. These can also be called measures. This slide shows 3 different noise descriptors: Lmax, Lx, and the LEQ. The Lmax, or maximum noise level, is the highest instantaneous noise level during a specific time period. The use of peak level is discouraged because it may be interpreted as a non-RMS noise signal. Lx is a statistical descriptor where the noise level exceeds X% of a specific time period. The value of X is commonly 10. Other values of 50 and 90 are sometimes also used. For example, this could be L sub 10, L sub 50, and L sub 90. The LEQ is the equivalent noise level. This descriptor is routinely used by the Florida Department of Transportation and the Federal Highway Administration to address the worst noise hour. The LEQ is the equivalent steady-state noise level in a stated period of time that would contain the same acoustic energy as the time-varying noise level during the same period. Continuing on with more descriptors, this slide shows 3 more noise descriptors: the LDN, the CNEL, and the SEL. The LDN is the day-night noise level. This is used commonly for describing communities' noise level. The LDN is a 24-hour LEQ with a penalty of 10 decibels added during the night hours from 10 p.m. to 7 a.m. The penalty is added because this time is normally sleeping time. The CNEL is the community noise equivalent level. This is common community noise descriptors and is also used for airport noise. The CNEL is the same as the LDN with an additional penalty of 4.77 decibels, or 10 to the log of 3, for the hours between 7 p.m. to 10 p.m., which are usually reserved for relaxation, TV, reading, and conversation. The SEL is a single event level, which is mainly used for aircraft noise. The SEL enables comparing noise created by a loud but fast overflight with that of a quieter but slower overflight. The SEL is the acoustic energy during a single noise event, which, as an aircraft overflight, compresses into a period of basically 1 second and expressed in decibels. Which descriptor does the Florida Department of Transportation use to describe highway traffic noise? The LEQ hourly. 23 CFR Part 772 specifies that either the LEQ hourly or the L10 hourly metric can be used, but not both. FDOT uses LEQ hourly. LEQ hourly is typically 3 decibels less than the L10 for the same conditions. So let's move on to sound propagation. What is sound propagation, you ask? It is the manner in which sound travels through a compressed medium such as air. Propagation is influenced by a variety of factors, including geometric spreading from point and line sources, ground effects, atmospheric effects, and shielding, both natural as well as man-made features. Note the increasing size of the wave as it moves outward from the source in the center. There are two primary types of geometric spreading: spherical spreading and cylindrical spreading. Spherical spreading originates from a point source such as pile driving. Cylindrical spreading originates from a line source such as traffic. Point sources are stationary. The sound propagation radiates outward uniformly from the source in a spherical pattern. The sound level attenuates or decreases at a rate of 6 decibels for each doubling of the distance from the source. A line source such as highway traffic makes the sound appear to emanate from a line rather than a point, which results in cylindrical spreading. The sound level attenuates at a drop-off rate of 3 decibels for each doubling of distance. Note that a line source is a series of moving point sources, and the drop-off rate is not the same as that for a point source. Receptors versus receiver. Oftentimes, these two words are used interchangeably. However, there are some instances which require the use of one word over the other. Receptors are discrete or representative locations in a noise-sensitive area for land use listed in the FHWA NAC table. They are specific XY points in the traffic noise model from which traffic noise values are predicted. On the other hand, the receiver is a physical, real-life recipient of noise such as a human or animal ear. Ground absorption also affects noise. Ground absorption is how the ground surface tends to absorb or reflect traffic noise. In general, there are two types of classifications for ground surface types: hard sites and soft sites. Hard sites are typically more reflective. Soft sites are acoustically more absorptive. Additionally, the drop-off rate depends on if it is a point source or moving line source. A hard site is a reflective ground surface between the source and the receptor, such as a parking lot, which is made from concrete, asphalt, etc., or water. The hard surface drop-off rate for a moving line source is typically considered to be about 3 decibel per doubling of distance. A soft site is an absorptive ground surface between the source and the receptor, such as grass or lawn, loose soil, and even snow. The soft site drop-off rate for a moving line source is typically considered to be about 4.5 to 6 decibels per doubling of distance. Let's do an exercise together. Calculate the noise level from a point source to a receptor 200 feet away if the noise level at 50 feet is 76 decibels. Assume the ground surface is soft and assume the drop-off rate is 6 decibels per doubling of distance. Just to be clear, we do not model point sources for traffic noise, only lines. At 100 feet away, the noise level is 70 decibels, and at 200 feet away, the noise level is 64 decibels. Let's try another problem. Calculate the noise level from a line source to a receptor 400 feet away if the noise level at 50 feet is 76 decibel. Assume this is a hard site with a drop-off rate of 3 decibel per doubling of distance. At 100 feet, the noise level would be 73 decibels. At 200 feet, the noise level is 70 decibels, and at 400 feet, the noise level would be 67 decibels. But what would you get if this were a soft site area, assuming the drop-off rate of 6 decibels per doubling of distance? At 100 feet, the noise level would be 70 decibels. At 200 feet, the noise level is 64 decibels, and at 400 feet, the noise level would be reduced to 58 decibels. What is shielding? Shielding is some object that exists between the noise source and the receiver that can reduce overall noise level. Shielding from traffic noise can occur from a single or multiple buildings, rows of homes, noise barriers, earth berms, etc. Examples of shielding include buildings, rows of homes, or existing barriers. Note that the reduction provided by each will vary. Vegetation and landscaping, such as clumping bamboo, although beautiful, is not considered to be a form of abatement because it typically doesn't provide enough noise reduction. A note about vegetation and traffic noise. To reduce traffic noise, according to the Federal Highway Administration, Vegetation must be 200 feet deep and optically dense, as in you must not be able to see through it, in order to provide a 10 decibel reduction. Typical vegetation, even though it may not measurably reduce the noise, may provide a visual block that provides a perceived psychological noise reduction. Typical Florida vegetation and Florida DOT landscaping do not do much to reduce noise levels, but provides a psychological benefit. Vegetation is more likely to provide a 1 to 2 decibel reduction, although it can vary considerably depending on the thickness and the type of trees and the type of leaves. To be considered acoustically benefit, the leaves must retain throughout the year, so they have to be evergreen. Removal of the trees can be expected to increase noise complaints even if it can't measure the increase of noise with a noise meter. This is because there may be some frequency shift as a result of vegetation that cause the noise level to be more acceptable with the trees present. Minimizing vegetation removal can be a positive step in reducing noise complaints. Buildings and rows of homes can provide shielding. The shielding provided depends on the size of the structures and the spacing between them. Shielding values generally are on the order of 3 to 5 decibels per row of homes, up to a maximum of 10 decibels. Shielding can be provided by roadway features such as an elevated roadway on fill or embankment, elevated roadways on mechanical stabilized earth or retaining walls, and the top edge of a depressed roadway or roadway that is in a cut section such as the picture shown at the bottom right. Shielding from building envelopes or exterior-interior reductions will depend on the building construction and the amount of open or closed windows. However, it should be noted that open windows are not modeled when modeling highway traffic noise. The amount of noise reduction that is provided by a building depends on the building type, window type, and whether the windows are open or closed. The reduction of interior levels is based on the surrounding walls, especially those directly between the source and the receiver. For example, a masonry building with a single glazed window provides a 25 decibel noise reduction due to the building structure. Importantly, it is generally assumed in Florida that windows are kept shut most of the year. With this heat and humidity, why would anyone want to open windows in Florida? But I digress. Finally, noise barriers are the last type of shielding that will be discussed in this training. How do noise barriers work? Glad you asked. By interrupting the direct noise path between the source and the receiver. There is a direct correlation between the shadow zone and diffraction. Diffraction is the bending of the sound waves around an obstacle which causes the sound wave to take on a longer path. This happens at the top and sides of a barrier. Higher frequencies have a shorter wavelength and therefore diffract to a lesser degree than longer and lower frequencies, which go deeper into the shadow zone. Therefore, barriers are better at attenuating higher frequencies than they are lower frequencies. Insertion loss is the difference in the noise level from the before barrier and after barrier conditions. This is also referred to as the noise reduction and includes all of the things we have discussed, including ground attenuation, reflection, diffraction, and absorption. Noise barriers should be placed as close to the receiver as possible. If it is not possible, then the noise barrier should be placed as close to the roadway as possible. The noise barrier should not be placed in the middle between the roadway and the receiver. Keep in mind, if there's a large space between the source or roadway and the receiver, the sound waves will spread out. If the roadway is depressed, the noise barrier should be placed at the top of the cut slope if possible. Placing the barrier at the top of the slope reduces the required height and increases its effectiveness. The barrier is mostly ineffective if you can see the traffic. If there is a line of sight from the receiver to the traffic, there is little to no abatement. However, blocking the view of residents may become an issue in some states and may result in the use of transparent barriers. Additionally, placement on the top of the slope reduces safety issues. If the roadway is elevated, the noise barrier should be placed as close to the road as possible. Placing a barrier near an elevated roadway can reduce the required height of the road considerably compared to a ground-mounted barrier. Additionally, wall heights may be limited due to structural and safety issues. This will be discussed in a later lesson. Also, walls on structure may block a vista for motorists. How tall does a noise barrier have to be? Many factors influence the height, but the general rule of thumb is that a noise barrier has to be at least able to break the line of sight to achieve a 5 decibel reduction in traffic noise. Furthermore, for each 2 feet above the initial break in the line of sight, you will achieve approximately an additional 1 decibel reduction in traffic noise. Note that breaking the line of sight for traffic noise involves multiple sources, including tires, the pavement, engine exhaust, and heavy truck exhaust, in which is almost 12 feet above pavement. For example, this is not an effective noise barrier design. If you can see the source, there is not much noise reduction, if any at all. How long should a noise barrier be? Good question. As with height, many factors will influence the length. The general rule is that the barrier should extend 4D beyond the receptor. What is 4D? 4D refers to the distance between the end of the barrier and the last receptor. The end of the barrier should be at least 4 times the distance as the last receiver is perpendicular to the barrier, as shown in this figure. This is because of diffraction. Yes, we've reached our conclusion. If you have any questions, please feel free to send an email to oem@dot.state.fl.us.